All right. Welcome to, man, I feel bad. It must be boring this year. The class is getting smaller and smaller. Is it Friday? Is that the problem? Okay. Well, it is Friday, so that's a good thing, I guess. And it's better for some people than others. It's better for you guys because you chose to come to class on Friday, which is great. So everybody here gets an A. Pretty easy. All right. Yeah, there we go. A grade of some kind. All right, so today we're going to talk. So last time we did this whirlwind introduction to the synchronization primitives that you'll be using to solve synchronization problems, not only as part of assignment 1, which hopefully you guys are sort of in the process of wrapping up, but also as part of assignment 2, which will be starting in recitations next week. So again, the recitations are sort of designed to give you a feeling for where you're supposed to be. There's 3 weeks till the first big deadline in the class, which is enough time to do assignment 2. And but first of all, we're going to talk about a couple of problems with some of the primitives that we've outlined, right? So pitfalls that you can run into while using them, and then a couple of simple solutions. Then we're going to do 2 examples in class showing sort of ways to use synchronization primitives. So we'll do a couple of little coding examples and give you an idea about how to solve a couple of sort of classic synchronization problems. One of them will be this sort of bounded buffer producer consumer that we've been sort of conceptualizing but haven't really looked at code for. And then I'll do a couple of quick examples with semaphores just to give you some sense of when semaphores could potentially be useful. And then finally, there'll be a little bit more advice at the end of class about how to choose the right synchronization primitive. All right. So like I said, next week the recitations will start to cover assignment material for assignment 2. If you're not at that point, then I don't know what to tell you. I mean, we have to keep the recitations moving so that we can give you enough time to get assignment 2 done, right? On Wednesday and Friday next week, I won't be here talking to you in person. I'm going to be traveling. What I'm going to do is the following. So I think if I'm careful today, and we might finish a little early today, and the timing might be a little weird today and Monday, but I'm going to try to get us to the point where I can assign sort of 2 full lecture videos from 2013. So hopefully next week will get us through scheduling, and on Wednesday and Friday you'll be watching this. On Monday we'll do sort of an introduction to scheduling. On Wednesday you guys will watch a video about a couple of sort of classic scheduling algorithms and talk about how to evaluate scheduling algorithms. And Friday's lecture is kind of a fun lecture about the recent history of the Linux scheduling subsystem and Linux schedulers. And it's my only chance to swear at you in class for a legitimate reason. So sadly, I won't be able to do that next Friday, but the video will be doing that. However, rather than just watch movies and lecture, which sounds a little bit dull, what we're going to try is on Friday, we're going to do a design document exercise for assignment 2, right? So the videos that are assigned are going to be things that I'm going to expect you guys to watch. So there will be questions about them on the exam. These are not optional, right? On Wednesday, what we'll do is please bring a design document or some notes or some idea of what you're going to submit for your assignment 2 design doc to class with you. And what we'll do is that Jinghao and Zihei and hopefully some of the ninjas who are available will come in and help you guys sort of pair up into pairs of pairs and talk over your designs with other students to get some feedback and to talk through some of the common issues. So, again, hopefully this is something that you guys will find useful, and that's what we'll do on Wednesday. And then Friday, I don't know what we'll do. It's possible, Jinghao has talked about potentially just doing another recitation during class hours, answering questions about assignment 2 or doing something like that. But it's also possible that we'll just give you Friday off, which would be nice. But we'll see. So keep an eye on Piazza and wait to hear from us. All right, so this is next week. And then happily, I'll be back on the Monday following, and we will start on VM. And I'm really glad that this trip didn't interfere with my ability to do the VM lectures, because I really like VM. All right. So any questions about last time? We actually did locks. That was maybe 2 times ago. We did locks, condition variables, semaphores. It's kind of a quick and dirty introduction to these primitives, but many of you guys are probably seeing them as part of assignment 1. So any questions about this before we go on? Yeah?
Did we actually mention when we would want to be spinning versus sleeping?
Did we mention when we wanted to be spinning versus sleeping? Yeah. I see heads going up and down. Yeah, in fact, there's good question about this, right? So spinning versus sleeping. Thank you for segueing me so nicely to my next slide. So spinning, so remember we looked at two ways to implement locks, right? Or two ways to implement the mutual exclusion that you needed for critical sections. One way was to spin, namely to sort of repeatedly try to request a resource until it becomes available. And the other way was to go to sleep and wait for the resource to become available, right? Wait for the kernel to wake me up, or for some other thread who's accessing the resources to wake me up when it's finished using, right? So where is spinning almost never a good idea? Yeah, on a single processor system, because normally when you're spinning on a single processor system, you're preventing the thread that has the resource from making progress. And if you prevent it from making progress, it's going to hold the resource longer. So all the time you spend spinning is just adding to the time that you're going to be waiting. The best thing to do is to not spin, just go to sleep, and wake up when the resource becomes available. However, there was an interesting trade-off here in certain cases where I might actually want to use a spin lock. Does anyone remember? Yeah, Cyril. Yeah, if the critical section is short, then it's possible that the context switch overhead will actually overwhelm it will be slower to context switch than it will be to just run that test instead a few more times, right? So in that case, it's possible that as long as the critical section is only a couple of instructions, then spinning is the right thing to do, right? And if you look at our implementation of spin locks for OS 161 and where they're used in the code, specifically in the semaphore code that we provided as an example for how to do some of these things, they're used to protect just a couple of instructions that are just modifying some memory, right? So that critical section ends fast. There's no sleeping. There's no blocking, and that's good. And if the critical section is quite long, if I have to do I/O, if I have a lot of logic inside the critical section, I have loops or other things that could potentially take a long time, then it's probably better to put myself to sleep and wait for someone else to finish using the resource rather than spinning. All right? I just told you why. All right, okay. All right, so what about, let's just do a quick review of locks, right? So what was the lock interface? Acquire and release, right? So lock acquire can acquire the lock, sleeping if necessary. This is sort of the lock interface to the sleep-based locks that we've given you or we've asked you to implement for assignment 1. And then lock release will not, man, I can't believe this. It's like the 3rd year in a row I've had this bug on the slide. And I always say I'm going to fix it. Clearly that's wrong, right? So that would release the lock rather than acquiring it. And it will not sleep, right? Lock release should not sleep. It doesn't need to. What are locks for? What's one of the primary reasons that we use locks? Yeah, Arya. Yeah, he's reading ahead on the slides. Yeah, to protect critical sections, right? Look at that. Wow, you read my mind. And really to protect any sort of shared state, right? So the critical section abstraction is sort of treating a piece of code as a shared state, but I can actually have the same lock used multiple places to protect one sort of shared data structure, right? Even if that data structure is being accessed in different ways, right? All right, any questions about locks before we keep going? All right, so here's one problem I can have with locks, right? So locks sound awesome, right? I mean, locks are this, and now that we've given you this hammer, it's possible that you're going to find lots of nails in your code, right? So, hey, I've got these locks now, and it's going to help me solve these synchronization issues and help me address race conditions. So I'll just start putting them all over the place, right? Lock this, lock that, Put locks on lots of stuff, right? I mean, it's kind of cool, right? It's like, now it's mine, I got a lock on it, can't have it. And in some cases, threads legitimately need multiple locks to access a certain set of shared resources, right? So I might need one lock to do one thing and another lock to do another. And actually, in certain cases for safety, I might have to hold both of those locks at the same time, right? And so let's consider this particular case, right? So I've got two resources 1 and 2, very exciting resources, clearly that I need a lock for, right? Because I wouldn't want anyone to take my 2. And so let's see what happens, right? So and I have 2 threads that are competing for these shared resources, right? And I'm using a lock to protect each one, right? Why wouldn't, so let me just ask you something. As a programmer, why not just use one lock to protect both of these resources? Wouldn't that be better? In what case would it be better, Scott?
Well, would it be better if both resources were always used, like always ready together?
Yeah, so if both these resources are essentially always accessed together, then I really shouldn't use two locks, right? I should just have one lock to protect both of them. Why in some cases would I need two locks? Yeah, Chris.
If the resources are used separately and there's one lock in both resources?
Right, so if resource 1 and 2 can be used independently, but then are sometimes used together, then this is a better pattern, right? So, if possible, it would be better to put these under the same lock, but the premise of this example is that that's not possible, right? I need two locks, one for each resource. But sometimes I need both resources, okay? So let's imagine that thread A runs and it grabs the lock for resource 1, right? And now there's a context switch, and thread B runs and grabs the lock for resource 2. Okay? Can anyone see how this is going to end badly? Right? So now thread A runs, and it tries to acquire a lock for resource 2. And what's going to happen at this point? It's going to, well, don't get too far ahead of me. Right? Okay, I'm going through this slowly so I can understand it. It's going to go to sleep, right? It's going to sleep because that's the lock interface. Lock 2 is held. So now what happens next? Thread B runs, and it tries to acquire the lock for resource 1, and thread B sleeps, right? And now what happens? Well, I mean, nothing, really. I mean, if these were the only two threads on the system. But I think people have been doing assignment 1. This is the first year that I'm ahead of assignment 1. Sorry, assignment 1 is ahead of me. So it's kind of fun because people actually know this stuff. OK, so yeah, this is what's called deadlock, right? And one way of thinking about, what's one way of sort of, conceptually describing a deadlock, right? A deadlock refers to a what in the waiting queue, right? If I was able to look at the waiting queue here, what would I see?
Circle dependency.
Yeah, I would see somebody whispering. What's her name? Something. So a circular dependency, right? I've got two threads on the wait queue that are both waiting for each other. And the problem here is if you're on the wait queue and you're waiting for someone who's also waiting, and if that person is waiting for someone who's also waiting, and if that person is waiting for you, then there's no one is going to get into this little weird circle of people who are waiting in order to wake anybody up, right? And these two threads will sleep forever, right? So, yeah, and one way of describing a deadlock it occurs with a thread or set of threads are waiting for each other to finish, and thus nobody ever does, right? However, it doesn't actually, this is a fun example, it doesn't actually require more than one thread to deadlock. How can I deadlock a single thread? Yeah, Doug.
If I think I got this a lot with spin locks.
Uh-huh.
If you try to spin lock when you already have the spin lock.
Yeah. So if I try to grab a lock I already hold, right? Then I've got a circular dependency, and it's just all pointed right back at me, right? I'm waiting for me. Now this sounds really stupid, right? How would this ever happen, right? It's not like you would like write a block of code that says lock acquire lock A, and then right underneath it lock acquire lock A, right? I mean, who would write that stupid, idiotic piece of code, right? People do write stupid pieces of code like that, but not you guys, of course. So how would this happen? This does happen, actually, but why, right? Why other than like incredibly inane programming? Yeah?
You forget to release the rock and you again go back.
It's not, that could happen. That's not what I'm thinking of, though. Yeah?
Having a counter so that how many times you have blocked the resource so that...
No, you're solving the problem already. I don't want that. I don't know how the problem happens, right? Yeah?
Maybe it's just the fact that like the lock and the unlock would be far apart in code, and so like you're not seeing them close together.
Yeah, well, okay. Well, what's a common way for that to happen, right? As a programmer, I grab a lock and then I start doing some stuff. What in particular could I do that would cause me to maybe not to self-deadlock? Yeah.
Single thread, this can happen if a single thread has like multiple locks.
Yeah, it's not even multiple locks. This happens with one lock. Yeah.
You call a function when you already have a lock, which
Yeah, that's the classic example, right? I call a function, and I don't know what the function does, right? I'm just calling it. My partner wrote it for assignment 2, right? Do get good grade on assignment 2 function. I called that. And it turned out that that function grabs all sorts of locks, right? And one of the locks it grabs is one that I already hold, right? And there's a classic solution to this that someone suggested over there, which is to have what are called recursive locks, right? That can be locked multiple times as long as the same thread unlocks them multiple times. The lock that we gave you does not do that. And it should not do that, in fact, because there's times when you want a recursive lock, and there's other times when using a lock like this and having it lock, again, by the same thread is a programming bug, right? So remember, particularly in the kernel, and this is something that I'm sure that Jinghao and Guru have told you in recitation, defensive programming wins, right? If I have an interface that's supposed to be used a certain way, and you do something that's not supposed to happen, you shouldn't just be like, whatever, I'll just let it slide this one time. You forgot to release the lock, but that's OK. I'll just let you acquire it again, right? No, panic, right? Because you want to know as a programmer that you're not using the lock properly, right? Right, so this is I just talked through all this. Recursive locks, right? Yeah, so as long as I pair calls to acquire and release, I can do this, right? And recursive blocks are frequently used in parts of code where there's a lot of complex dependencies and where code can call other code. And once the function chains get long enough, sometimes this is a good solution to this problem. It's not always a good solution to the problem, right? All right, so there are 3 conditions that must be met in order for a deadlock to occur, right? The first one is simple, right? Some protected access to shared resources. This is why we're using a lock in the first place, right? I have a shared resource that I'm trying to synchronize. If I don't have locks, then I can't deadlock, right? Actually, I shouldn't say there are 3 or 4. So there's also this no concept of resource preemption, okay? Up until now, and this is the way to think about it, we've associated the concept of lock with with exclusive ownership, right? If thread A has a lock, thread B just can't come over and and whack it and take its lock away, right? There's no way to do that, right? You could potentially implement that in a certain way, but it would be kind of hairy to get right? Multiple independent requests. So I have to actually be able to acquire another lock once I have the first lock, right? And each one of these is sort of giving hints about ways to address these problems, right? A lot of these hints are, first of all, if you have shared resources, they need to be synchronized. So number 1 is pretty much off the table, right? If you want to try to get number 2 to work, be my guest, right? My guess is that's going to be terrible to do, right? Because how am I supposed to take a lock away from a thread? It's halfway done with what it's doing, right? And the problem is, that can almost start to look like the thread not having the lock in the first place. The data structure gets left in some sort of weird, inconsistent state, which was what I was trying to use the lock to prevent, right? Here, you can potentially write a function that just tries to grab a bunch of locks all at once, right? That could potentially be useful. That's not really that pretty, right? This is usually the place where we can get out of the deadlock issue, right? Which is to eliminate the circular dependency, right? But this is also required for deadlock, right? So if you see this question on exam, you know what the conditions are. If I don't have a circular dependency graph, then I cannot deadlock, right? At some point, when I start acquiring locks, I have to sort of loop around so that I can have a group of threads that are all waiting on each other, right? And that circular dependency graph can get quite big. It's usually not very big. It's usually 2 threads, right? All right, so, and this is this is sort of like the classic synchronization problem, which I feel like if I didn't talk about this, you guys would think, I took this course on operating systems, and we never talked about the dining philosophers problem, and I felt really disappointed, right? So because I want good course evaluations, I'm going to talk about the dining philosophers problem. So I have my philosophers, and maybe some of you can identify some of them. I used to know who all 5 were, but I've forgotten. I think that's Francis Bacon. That's Isaac Newton, Descartes. Not sure. Challen? Yeah. Oh, wow. Apparently somebody wants to give me a good course evaluation too, which is great. Paired resource request and resource fulfillment. Okay. So, imagine that these philosophers have met to have dinner, and each one of them needs 2 chopsticks or implements. I don't know why chopsticks. Chopsticks, clearly you need 2 chopsticks. So that's a good example, right? You need 2 chopsticks. 1 chopstick's not very useful. And here's what happens. So they sit down to eat, and each one of them grabs the chopstick while they also change sizes, which is great. Each one of them grabs the chopstick next to them, and now I have a deadlock, right? So this is the classic sort of round the table deadlock condition, right? And then you can think about how I would break out of this using each one of the conditions, right? So remember, if I relax any of those 4 conditions, then there cannot be deadlock, okay? So the first thing is, if I can't wait, if I don't wait, right? And this is, essentially the first condition, then it's possible that eventually somebody will get 2 chopsticks, right? So if I grab the first chopstick, and then I check to see if I can get the second one, and if I can't, I just drop the first chopstick, right? And I do this, with some random delay built in. So finally, somebody gets 2 chopsticks, right? And then maybe someone else gets 2 chopsticks, and they can actually make forward progress, right? So this is one way to do this. The problem, of course, is, does, for example, with the locks we gave you to implement for OS 161, do they have any way to check whether or not they're required? No, they're not supposed to, because you're not supposed to do this with them, right? You can't check to see if their resource is busy. It's possible to be useful, but in this particular case, we're asking you to use them in a way that prevents you from doing this, right? So the second way is to implement some new mechanism so I can simultaneously, whatever that means, I have to have something that allows me to create this notion of atomicity, grab both chopsticks, right? So I grab both chopsticks together, and now, because I can never hold one chopstick, I don't have this problem, right? But this is usually the most useful way to break out of deadlock, and that's to establish a locking order, right? Or a lock priority, which means that whenever I need a certain set of resources, I'm always going to grab them in a particular order. So if I need resource A and resource B, I'm always going to lock resource A before I lock resource B. If you remember our original example, if those 2 threads did this, then it's possible that they wouldn't deadlock. I shouldn't say it's possible, they would never deadlock. And even the Dynean philosophers who have this, who have this even more complicated case where there's like a bunch of different, where did they go? There they are. Where I have 5 resources, right? Even here you can establish a locking order, right? Okay. And the locking order could be, I number the chopsticks in some way, and then I always grab the highest numbered chopstick first, right? So everybody at the table is going to grab one of the chopsticks first, maybe the chopstick on the left, except for one guy, right? Everyone grabs left first except for one guy at the table, and he tries to grab the right one, right? He's gonna, he's not gonna get that chopstick, and that's gonna break the cycle, right? And then the last thing you can do, and certain systems do this, is essentially try to detect deadlocks, right? So detect deadlocks internally, see that there's a deadlock that's formed because of the pattern of access to a certain set of resources, and then take one of the chopsticks away from one of the philosophers and allow the deadlock to be prevented. But this is usually not a very good idea, right? This requires a lot more mechanism than you guys are going to have at your disposal, right? So this, breaking cycles is definitely the superior way of doing this, right? All right, so deadlock is, so starvation is this problem that some of you guys may be experiencing as you think about reader-writer locks, right? And starvation is a different type of condition than deadlock, right? So in deadlock, nobody's making progress because everybody's sleeping, right? That's a definition of a deadlock. I have everybody on the wait queue and no one's actually running, right? Because everybody's waiting for each other to do something. Starvation happens when there are threads that are making progress, but not all of them. And starvation happens in particular when there's a certain set of threads that under a certain condition could prevent other threads from ever making progress, right? And it can be very, very hard to eliminate starvation entirely, right? And so normally what we try to do is create conditions where starvation is unlikely to happen based on our understanding of the system, right? Usually whenever I have any sort of prioritization of resources, it's possible that some threads or processes can be starved, right? And what I use to sort of allow processes to make forward progress is simply an assumption that eventually the high priority sort of process or thread will finish what it's doing, and that'll allow the lower priority ones to move, right? All right, so let's go back to deadlock. So as a programmer, I'm giving you 2 choices, right? These are not very good choices, right? But which one is better? A deadlock or a race condition, right? Because you can think about it, deadlock as occurring from potentially having too much synchronization, right? Sometimes as you work on problems and keep adding locks, eventually you'll have a deadlock, right? Because you'll put a lock somewhere and you won't realize that you're holding another lock and someone else is acquiring them in a different order, and and now you'll have a deadlock. But what would you prefer as a programmer? A deadlock or a race condition? Yeah.
A deadlock,
Why?
because it guarantees correctness.
Well, a deadlock, I mean, let's put it this way. Deadlocks are not correct, right? It is not correct for nobody to be eating, right? Someone should be eating.
It won't let something wrong happen to the, I mean, it won't input wrong data into whatever you are doing.
Okay, but again, if you imagine that one of the requirements of your code is that it continue to execute, right? Then I would argue that it's not correct for it to just stop and do nothing, right? You're right that it doesn't cause sort of data corruption, right? But there's something else I'm getting at here. Yeah.
We get to know that there is some problem
Why?
because there is a deadlock in some happening.
Yeah. So the correct answer here is at least me, right? You guys can make your own minds about this, but deadlocks are typically much easier to detect, right? A race condition can cause something to be weird, right? And maybe the program continues to use these values and ends up just making wrong decisions or behaving erratically, right? Whereas as a deadlock, everything stops, right? And that's weird, but the nice thing about deadlocks is they just stay that way, right? Once your system is in deadlock, it'll just lie there, right? Doing nothing. And then you can, even if it's like 10 minutes later, you can come up and be like, this is weird. My system is not doing anything. I wonder what's happening, right? So, and some of you guys will start to see this. Maybe how many people have already produced some kind of deadlock as they've been working on assignment 1? Yeah, and it's actually pretty easy to tell because you're like, oh man, I knew sys 161 was slow, but this is unusually slow, right? And so yeah, so deadlock is usually preferable to race condition. So a little bit more, too much synchronization is definitely preferable to not enough, right? So we'll come back to this a little bit maybe when we talk about thread scheduling next week. But I just want to point out another kind of fun problem that synchronization can create, which is a case called priority inversion, right? So priority inversion essentially occurs when synchronization, right, the process of synchronization frustrates the operating system scheduler's goal, which we'll talk about more next week, of prioritizing access to resources based on some scheme, right? So you can imagine I have some tasks on my system that someone has told me, hopefully you, the user, these are important tasks, and then I have other stuff that's supposed to run in the background. And so, all operating systems have these notions of priorities and use those priorities to determine how tasks and processes gain access to resources, right? And again, so priority inversion means the operating system said this thread is higher priority than this thread, but due to some use of a synchronization primitive, the opposite ended up happening, and the lower priority thread ended up being granted more access to resources, right? So here's the, and actually, I think this will be in the video next year, but this problem has actually manifested itself in the real world. Was anyone familiar with this? Maybe this is when you guys were like in diapers or something, but yeah, Mac. Yeah, so there was a Mars, one of the Mars rovers suffered from this problem, actually, or a variant of this problem. And it actually crippled it for a period of time until they were able to sort of fix it from Earth, which is pretty awesome. That is remote debugging. So let's, and so for this example, and this actually is drawn from the Mars rovers sort of as a model, assume that I have a strict prioritization between threads. This isn't actually how real systems or the systems you guys are used to working with typically do things. But assume that when I'm thinking about which thread should gain access to the CPU, if the high priority thread is able to run, it will always preempt threads with lower priority. And if a thread, and this works all the way down the chain. So the high priority thread will always gain access to the CPU if it needs it, and the medium thread has to wait for it, and the low priority thread has to wait for the medium priority thread, right? So let's imagine that this happens, right? So the low priority thread runs, and it grabs some lock on the system, right? A lock that's protecting access to a resource. And now let's say the low priority thread is preempted by the medium priority thread. The medium priority thread wakes up and is now able to run, right? So the medium priority thread starts running. And so the low priority thread is stopped, and it's stopped with what? It's stopped with the lock, right? So it's holding the lock, but it's not running, right? Now, the high priority thread is now ready to run, and so it preempts the medium priority thread, but it turns out it actually needs the resource that the low priority thread has, right? And so it blocks. But let's say that the medium priority thread is still ready to run. Well, who's going to run next? Yeah, and if the medium priority thread always has work to do, right? I think this is what happened with the Mars rover. It was a long running thread. It was doing a bunch of stuff. It could potentially keep the high priority, and what's happened here, right? The high priority thread has work to do, right? But because of the use of a synchronization primitive, it's actually being preempted by the low priority thread, right? So this is the opposite of what the operating system wanted to happen. It wanted the high priority thread to have higher priority access to the resources on the machine, but because of this problem, it's blocked, and the medium priority thread is just hanging out. It's like, this is awesome. I don't know what happened to that high priority guy, but this machine's all mine now, right? And a really clever solution that some systems implement to deal with this is this notion of priority inheritance, right? Simply put, when a high priority thread is waiting for something, or for some other thread that holds a resource, that thread now inherits the priority of the thread that's waiting for it, right? So if the high priority thread had allowed the low priority thread to borrow its priority, Guru. Yeah? Yeah? Oh, no, you need more of a mechanism for this, right? You certainly, Guru's right. I mean, the operating system here certainly needs a way to detect, right, that the high priority thread is blocked by the low priority thread. If I can't detect that, then I'm stuck, right? So yeah, I mean, on your system, you don't have any way of determining that right now, but you might, actually. You might. This might be not as hard to do as I'm thinking, right? You can certainly look at the wait channel and say, aha, there's these threads on the wait channel with these priorities. I'm going to give them all the priority of the highest priority thread that's there, right? But yeah, you certainly need a little bit more tools than you currently have. You wouldn't. This is not something that's implemented on OS 161. You'd have to do this, right? All right. Any questions about problems with synchronization, particularly with deadlock and that sort of stuff? All right, so now let's go through some examples, right? These are kind of fun. So this is what we've been talking about up till now. This is producer-consumer. What we're going to do is we're going to walk through a producer-to-consumer example and synchronize it, right? So we're going to take an unsynchronized producer-consumer and allow it to be synchronized properly so that they can use a shared buffer, right? So the shared state here is this fixed size buffer. Producers obviously can add items to the buffer if there's space. And consumers can withdraw items if there are items to withdraw, right? If a producer tries to produce into a buffer that's full, it has to wait until there's space. And consumers, I mean, I say must wait. They could certainly sit there spinning, trying to find something. But you might as well let them wait until there's items in the buffer to consume, right? So, and again, so this is when you start thinking about these problems, right? One thing that's important, as well as identifying the shared state and trying to figure out what your requirements are, is sort of looking through and thinking about everything you want to avoid, right? So if there's room in the buffer, I don't want producers to be asleep, right? As soon as there's room in the buffer, I should use it, if there are producers that are waiting to use the buffer. Similarly, if there are items in the buffer, I should not have consumers sleeping, right? As soon as there's something in the buffer, the consumer or a set of consumers should wake up to use it, right? All right, so here's my very simple beginning of an example here. The producer just puts item, I don't know, I probably would say item buffer, but whatever. Me 2 years ago said buffer item, so that's what we're using. And then the consumer just pulls an item out of the buffer and then either returns it or does some processing or whatever, right? So that's pretty simple. Mac?
Just nitpicking here, you have in the consume item, there's a time get
I know, gosh, I saw that too, but just nitpicky. Mac is nitpicking me. Yeah, don't try to run my slides, right? Do not try to compile and run these examples. No, I don't think any of them will compile it up, but yes. And it should just really be get buffer, right? Okay, anyway. So, what do I need to, so the first question I have is what do you guys feel like is the right synchronization primitive for this problem, right? Right? It's probably what?
Condition variable.
Yeah, so what's the condition that I'm,
Buffer is imperative or maximum.
yeah, so the condition here is the state of the buffer. What's the shared state that I'm going to protect? The buffer, right? The buffer, that's the thing that I need to make sure that probably only one thread is accessing the buffer at one time. If I was clever, I could probably figure out a way for two of them to be using the buffer, maybe different ends of it, but I'm not that clever. So, all right. So it's essentially up here, remember, I can't produce into the buffer until the buffer has space, right? And when I'm done, I'm going to increment the count of the buffer. So this is just the sort of the completion of the example, right? So while the count is full, I have to do something. And here, while there's nothing in the buffer, I have to wait, right? And once I pull an item out of the buffer, I need to decrement the count, right? So I've just introduced a new piece of shared state. What is that? The count, right? So that I need to make sure that I lock around the count so that the count is accessed properly, right? All right, so we said condition variables. I have the count, which is one piece of shared state, and conditions that require waiting, right? Full and empty, okay? So let's just fill in this example. So, you know, I think I need, so I have my count now, which I'm going to initialize to 0. I'm going to create a CV, right, to use for this. We said we're going to use a condition variable. What else do I need with a condition variable? Yeah, remember, a condition variable is always associated with the lock, right? Because a condition variable expresses change, is a signaling mechanism, right? And that's the best way to remember it. Condition variables are a signaling tool. They're a coordination tool. They do not ensure correctness. They're associated with the lock to make sure that you're using a lock as part of the condition variable, right? But they do not protect the shared state, okay? So before, up here in the producer, so what do I need to fill in here? What do I need to do before I check the count for sure? Yeah. Yeah, so before I check the count, I have to acquire the lock, right? If I don't do this, what could happen is I could check the count could be full, and I could go to sleep or wait, right? And then, but then right after I check the count, this guy could run, and he could actually consume something from the buffer, and there could be space, right? So I need to make sure that after, you know, that the count can't change on me after this condition, right? So using the condition variable, what am I going to do if the count is full? Yeah, I'm going to call CV wait, right? So there's a condition I'm waiting on. The condition is the state of count, right? The variable count. And I'm passing in the count lock so that the CV wait call can drop the lock for me, and then when I wake up, reacquire the lock, right? So, so, okay, so this makes sense to me the first time through, but then the next time this loop executes, why is it still safe? Remember, here I acquired the lock, and then I check the count, so that's good. I've got the lock for the count. Now I go to sleep. But when I go to sleep, I drop the lock. So the next time I wake up, isn't it not safe to check the count? Natasha?
Inside CV wait, when you wake up, it requires your lock.
Yeah, and there are actually CVs that are implemented differently here. There are some CVs actually that return without the lock, and you have to reacquire, right? But in this case, our CVs that we give you to implement will only wake up with the lock. So when they wake up, the first thing they do is grab the lock again. So every time I come through here, I have the lock. And every time I wait, I drop the lock, okay? All right, now down here, okay, so now I've dropped through my condition, meaning there's room in the buffer, right? What else is true as I put the item into the buffer and manipulate the count? What else do I have here that I need if I'm going to change the count?
Lock.
I still have the lock, right? Because CV wait return with the lock held, and so I still have the lock down here, right? Now, before I exit from produce, what do I need to do? Release the lock. That's important. What else? Yeah, I need to make sure, is that even on here? Oh, okay, sorry. I gave it away. Anyway, yeah, so I definitely need to release the lock. Let's just go through my stupid broken example, but I've given myself away about how it's broken, right? So consume looks quite similar, right? And we won't dwell on this, right? I acquire the lock. I need the lock to check the count. I do the same wait here, and I drop the lock here, right? And as someone has pointed out, there's something missing from this example, right? This example has properly synchronized the count shared state and the buffer. But what's not going to happen here? Yeah, so one thing I'll come back to in a minute is whenever you're using a condition variable, if you don't have a call to signal or broadcast, you're in trouble, right? It's like lock acquire and lock release. When you use a CV and you have a CV wait, there has to be a CV notify or a CV broadcast somewhere, right? If there isn't, you're just going to be waiting forever, right? So how do I do this? Where do I put these? Yeah, it doesn't look good. Yeah, better figure that out, right? So where do I put these calls to CV signal and CV broadcast, or CV broadcast? Well, but think about it, right? What expresses the condition here? The condition, the variable that's holding the condition is what? Well, that's not the, so there's, the condition is expressed on what variable, right? Count, right? So anytime I change the condition, I need to make sure that I send the signal, right? So one way to do this is this. And this is actually working code, right? This will run and it'll work okay, right? Every time I change the count, I broadcast because it's possible that the condition has changed, right? And remember, in order to broadcast, I need to hold the locks. I need to do that before I release the lock. And this code will work fine, right? But this code could be better, right? This code aspires to be better, right? What could I do if I wanted to, I just poked it. So what could I do if I wanted to be a little bit more clever here, right? What's that? No, I need the lock. Don't call CV broadcast, yeah. Yeah, because what's going to happen here, right? So it's possible that, let's say, right here. So when do I need to broadcast, right? I don't actually need to broadcast every time the count changes, right? I only need to signal or broadcast when? When the state of the buffer changes, right? Remember, the consumer only cares whether the buffer is full or not full. And the producer only cares whether the buffer is, the consumer only cares empty or not empty. The producer only cares full or not full, okay? And so if I'm clever here, I can put this statement in here. So what this means is if the buffer was empty and now it's not empty, then I want to wake up the consumers because there's now stuff to do. And down here, if the buffer was full and now has space in it, I can wake up the producers. So one last question, which is, I could do this, and this works fine, but why not? So CV broadcast, what's the potential problem here, right? What is CV broadcast going to do? So I know here that there's only one item in the buffer, right? Now the buffer used to be empty and now it has an item in, used to be empty and now it has an item in it, but how many consumers does it take to consume that one item? So I could use CV signal here, right? And that would be quote unquote more efficient. Well, it would be more efficient actually, I shouldn't say quote unquote, no scare quotes, that'd be more efficient. The only reason not to use CV signal is, because in some cases, I actually might want the operating system scheduler to be able to pick the next thread that gets to consumer produce, right? So if I call CV signal, what happens is the condition variable is going to pick, like, I don't know, some random thread, right? If I allow all the threads that are waiting, let's say I have some high priority consumers and some low priority consumers. If I wake up all the consumers, then I allow the scheduler to make the decision about which thread gets to consume, right? And in certain cases, that can be better. But this would work fine with CV signal in many cases. Right? Any other questions about this example? Yeah. Guy said, we're being yelled at, but I actually didn't yell. What was your question?
About why not use CV signal? If we say if the buffer is full and a consumer comes and picks up one, then if the consumer broadcasts, then the other, many other consumers can acquire the log, start decrementing at the same time. So that multiple threads can run.
Well, but again, the problem here is that if the count is 1, right, then there is.
So I was talking about the buffer being full.
Oh, down here?
Yeah.
Yeah. So it's the same thing. If there's only one spot in the buffer, right, then what will happen if I call broadcast is that every producer will wake up, but only one of them will actually fall through this loop,
But,
right?
Also, all the consumers should also wake up as well, right?
Oh, yeah. So that's a great point, right? So yes, I'm using one condition, right, for both sets of threads, right? On the other hand, if the count here was full, hopefully I don't have any consumers that are still waiting, right? Because the count's not 0, so those consumers should have fallen through already.
If you use CV signal and multiple producers come, then that might be the case that all the readers, all the consumers are waiting.
No, because if I'm down here, I shouldn't have any consumers waiting, right? Because those consumers won't call wait, right? I think if you work out how these interleave, you can convince yourself that there should only be consumers waiting if the count is 0. Right? Yeah. It's a good question, though. The other thing I could do to improve this example would be to use 2 condition variables, one for the buffer being full and one for being empty, right? And then I could potentially wake up fewer threads. Yeah?
Would it work if you switch the order of release and all that?
I don't think so, because I'm pretty sure that CV broadcast is supposed to make sure that the lock is held, right? So I need to broadcast before I call lock release. Yeah. Good questions. Any other questions about this example? All right, so let me do 2 minutes on semaphores, and I have 1 slide on this. Semaphores, again, because they have these looser semantics, the locks and condition variables, are not necessarily a great fit for a lot of problems, right? But let me give you one case where semaphores are useful, right? And actually, you see this in the code that we gave you. If you look at our test suites, you can see one potential use of semaphores, right? So the driver code creates a bunch of threads. It wants to let those threads run. But then when those threads exit, it wants to make sure to clean up the resources it's created for them to use, right? And the way that we do this is we create a semaphore. We initialize it to 0. Actually, that's not true. We have to initialize it to the number of threads. We pass the semaphore to each. No, actually, no, this is true. You initialize the semaphore to 0. I'm right. I'm right. Pass the semaphore to each thread. After I create in all the threads, basically, I go in a loop. I have to know how many threads are out there. And I just p the semaphore as many times as the number of threads I create, right? When the threads exit, they call v, right? And you can convince yourselves that every time one of the threads calls v, I get 1 iteration farther in the loop. When all the threads have called v, I can exit out of the loop, right? The final thing that you can use semaphores for, and don't run away because this is a hint for assignment 2, is in certain cases where you want to arrange synchronization between 2 threads, right? So let's say for whatever reason, I've created this, sorry, I want to use the pointer, not that thing. I have thread 1, and what thread 1 does is it forks another thread, thread 2. But then it's very important for thread 2 to wait for thread 1 to finish doing some stuff before thread 2 completes or does whatever else it's going to do, right? And one way to do this is by using semaphores as a form of a barrier, right? So I create a semaphore, I initialize it to 0. Thread 2, and thread can do a bunch of other stuff up here, right? But before it completes, or before it sort of does any other stuff that it can't do before I do this finish setup stuff, it calls p, right? And this will block. And the nice thing is, if thread 1 runs first and calls v, this will fall right through. If thread 2 runs first and calls p, it'll block until thread 1 finishes, right? So this is a nice design pattern. All right, so we talked about this a little bit last time, and I won't belabor it. Assignment 1, finish it up. On Monday, we will, those will be up. On Monday, we'll start talking about scheduling, and that's what we'll do next week. So have a great weekend.